talk about some of the more practical aspects of solving computational multiphysics problems. So the first thing that we're going to look at is something called a segregated solve. So bringing up the tutorial that we already previously talked about, which is the heat exchanger for the non-isothermal case. If you recall, this is the case where we have the heat transport that's going through the solid block. You have fluid channels going through the middle, and those fluid channels are importantly being forced on either side going forward and going backwards. Okay, so here's our coupling here. You may not have realized, but if you dig into the study, the solution, and the solver, you're going to see something different from pretty much every other tutorial that we've looked at so far, and that is the use of this segregated solver. The segregated solver, the idea is that if your physics are decoupled or decoupleable, then you can solve for one set of physics and then another and iterate back and forth until you arrive at the solution. And the advantage to this is there are a few. One is better memory usage. So because you're only solving for one problem and then another, you can compress that memory storage requirement, which is especially useful for big problems, obviously. Another important one is the ability to tailor your solver algorithm for a particular type of physics. That's generally speaking more into the realm of iterative solvers and preconditioners that we'll be talking about in numerical methods. Okay. In this particular case, because the fluid flow is being forced, and the heat transport is just happening and then is coupling to the fluid flow, it is weakly coupled. There is a coupling because the temperature is being carried away and the viscosity of the fluid, of the water, is temperature dependent. So there is a coupling, but because we're forced, it's weakly coupled and we can stand a chance of using the segregated solver. If, on the other hand, we were doing natural convection, or if there were big natural convective circuits that are being formed in here, cells, then we wouldn't be able to use this. We still could, of course, but it wouldn't have good convergence characteristics. So again, if you expand this, what you're going to see is the different steps here. Okay, a lot of this is going to be handled by COMSOL, especially by the templates that you'll be using, so you don't really need to worry about this sort of thing. But I do want you to be aware of that this is happening in the event that you see it or you're curious about what's happening or how it's being solved. Okay, so in the segregated solve, the first set of variables that you're solving is the velocity and the pressure, and then the temperature, and then you actually set a lower limit on the temperature. So if you've been playing around with natural convection, sometimes you see all of a sudden temperature having a massive excursion into negative thousands of Kelvin. This will block it. This will hold it steady. Okay, and then it cycles until everything is converged. And what we can do is go to compute. You can see there's going to be a lot of messages coming through the log here. That's because you're solving one, the other, the other, the other. And if you look on the convergence plot, you're actually going to see two lines here. Typically, you would only see one. And one is the temperature. Oops. One is the temperature, and the other one is the pressure slash volume, pressure slash velocity, as those are both converging and their error is approaching zero. Okay. The alternative to this is something called fully coupled, which, as the name suggests, if you go here and you hit fully coupled, as the name suggests, in this case, we are fully coupling the physics. Okay? So by selecting this and enabling it, it naturally deselects the segregated one because you can only have one. And now, when you go and you solve, what it's going to do is it's going to solve it all together as one. The solver in this particular case is a lot faster than the segregated solve, but the memory requirement was too fast to see, but it's going to be a lot more than the segregated solve was. Typically speaking, fully coupled systems are going to be more robust because you're completely capturing that whole coupling between the two different physics. Okay? But there's going to be a cost paid by your memory. Right. So the next thing that I wanted to talk about is a problem that's kind of common with multiphysics, and that is when you have two different time scales. Okay, so for temperature, heat balance, diffusion, typically you're about the same temperature, you're about the same time scale. But when you talk about something like elasticity, for example, elasticity travels elastic waves at the speed of sound in the material. When we go into electromagnetics, you're almost at the speed of light. Or dielectric material and charge redistribution, now you're at still very, very fast. So what we do, and we've already spoken about this, is you say that one of those physics is essentially happening so fast that it's basically static. It's basically a steady state. Now that doesn't mean that it's not changing with time. It just means because that time change comes from other conditions, other external impositions, your boundary conditions, volumetric conditions, time events, different physics coupling in there. But the phenomenon itself relaxes so fast that it may as well be steady state. We talked about this before, but I'm just going to show you where it is here. If you go under the physics mode and equation form, here you're going to see that it's study controlled. If you go to study, it says stationary, so guess what? It's going to be stationary. Watch what happens to this equation though if I expand it and hit time dependent. Now it's introducing the time dependent terms. Okay, this is how you would select between certain physics that's going to be happening in a time-dependent scenario versus the quasi-static. And it's called quasi-static again because it can change with time. It's just so fast that you may as well ignore that part. Okay, so let's go back to study controlled here. The final thing that I wanted to talk about today is something called variable scaling. Okay, scaling happens and is important when different physics are represented by field variables with different orders of magnitude. So in this particular case, we have the benefit of having a solution. If we look at the temperature, we see the temperature is about 300. We see that the velocity profile is about 0.1 meters per second, and the pressure is about 40. Okay. What you want to do, because your nonlinear solver is iterating on a guess, right? You can imagine it being here and looking over there for the next solution. If one of your field variables is much smaller than the other ones, for example, velocity, right, 0.1 versus 300 for temperature, you stand a risk of the solver moving in that direction and missing out a little bit on the velocity, right? It's going to be dominated by the temperature effect. It's going to be missing out a little bit on the velocity. So what you have to do, and we're going to be talking about this in numerical methods again, is you scale your variables. And basically what that means is that instead of solving for temperature, you solve for temperature divided by 300. Instead of solving for velocity, you solve for velocity divided by some constant, zero point 0.1. And if you get the right numbers there, if you get the right scales there, all of your variables are going to approach the number 1, right? There's nothing special about 1. It's just a convenient way to have all of your variables converging on the same order of magnitude. The key there is the order of magnitude. Again, we'll talk about that more in numerical methods. COMSOL, luckily for you, figures all this out pretty intelligently. There are a few ways to do that. So if you go under dependent variables here and look under scaling, you expand this. There is the option for automatic. Automatic basically looks at the material properties that you put in, the types of physics, and takes an educated guess. Right? There's some heuristics behind it. It's a decent guess. It's frequently wrong, to be honest, and sometimes significantly so, but for most of the applications that we're going to be using, it's good and it's reliable. An alternative is to use the initial value, right? And that makes a whole lot of sense, except for temperature, we could do that because in temperature, we set a reasonable initial value. For laminar flow, if you look at the initial value, we actually set 0 as our initial guess, right? 1 over 0 is going to give us not a number, it's going to be catastrophic. Okay, and this is common because unless you know which way the velocity is, in this case you do, but in general maybe you don't, right? If you're looking at some kind of cellular convection circuit or something, then you don't really have a good initial guess. Okay. The last thing that you could do is manually enter the scale for your variable. So if you do have some kind of idea on the temperature, the concentration, the speed for a hook or crook or however you get it, you can put that there. If you look under the log, I just want to show you a case example here. So here we had an automatic selection. There's scales for dependent variables here, and if we look at temperature, right, the code has found, the heuristics has found 290, which is actually a pretty good guess. It is roughly the right order of magnitude. The pressure, though, our answer is 40, and the guess was 3,700, right? Which is not great. But actually, the real problematic one here is the velocity field, right? The solution is zero point 0.1 order of magnitude, and this is 22,000. Okay, so this is actually pretty much exacerbating the problem. But because of the robustness of the fully coupled system, and actually also the segregated solve too, the way that it's set up, we don't need to worry about that so much. So typically you would just leave it this as automatic. If you have the benefit of some kind of preliminary solution, you might choose to put it in manually. The last thing that we're going to be talking about in lecture more, and I'm just going to highlight where you find it, is this thing called residual scaling. This is not typically modified. Automatic is generally the way to go, and that's because of the solver algorithms that you use. So I'm pointing this out here, but generally speaking, you won't have to use it.